Last section for solubility, let's go the opposite direction. So let's talk about precipitation. I've got my reaction here showing silver chloride dissolving into water. And so my first question is, which direction is precipitation? So take a look. When we're saying that something precipitates, that means it turns into a solid. So the reaction shifting to the left would be precipitation. So going to the right is dissolving, going to the left is precipitation. So my next question is, what can you calculate to predict which way a reaction moves? What do you already know how to calculate? Hopefully you remember Q. So the reaction quotient tells you where you are relative to where it wants to be. So the reaction quotient will tell you, could I dissolve more? Or if I try to put more in, is it going to precipitate? What is happening? Where am I? What's going on? So relative to, now we're just calling it KSP, but right, we can still do Q versus K. Q less than KSP, you would tell me the reaction moves to the right if you saw Q less than K. When Q is less than KSP, we call the solution unsaturated. It means that more can dissolve, right? Which is what you would have told me just from Q and K. Moving to the right is dissolving. It means we can dissolve more in solution. When Q is equal to KSP, well, that's at equilibrium. We call this kind of solution saturated. It means no more will dissolve. So we've dissolved the maximum amount, right? If one more molecule goes into solution, one molecule precipitates out of solution, we're at our dynamic equilibrium, and we call it saturated. Q greater than KSP. So, right, Q greater than KSP, you would tell me the reaction moves left, which means forming a precipitate in this case. And if you are under a set of conditions where Q is greater than KSP, we would call this a supersaturated solution. Now, you are probably wondering, how do you push a reaction to go beyond? Like, how do you get something that's supersaturated? Usually we do it with heat. So you can, because the equilibrium constant is temperature dependent, you can dissolve, typically you can dissolve more at a higher temperature than if you let it cool down undisturbed. You can have this unstable situation where more is dissolved in a solution than should be dissolved. And as soon as it has anything to like help seed the precipitation, or it gets disturbed in any way, all of that extra will precipitate out. So, I mean, let's predict some products. We've done this before, but let's do it with slightly soluble things or non-soluble things. So we're going to mix two solutions, one containing lead 2 nitrate and the other with sodium bromide, contains sodium bromide. Now we're just looking here, right? Lead 2 nitrate, nitrate salts are soluble. Sodium bromide, sodium salts and bromide salts are soluble, or at least bromide with sodium is soluble. So we're starting out with two just regular solutions. We're going to mix them together. And the new solution is 0.0150 molar in lead 2 nitrate and 0.00350 molar in sodium bromide. So the new solution we have concentrations for. Well, that's good. If you only have the original concentrations, you're going to have to do some dilution calculations first. But here we've just got the final concentrations. The question is, does a precipitate form? So first level, does a precipitate form, is just figure out the products and check the solubility rules. That we have done this before. So swapping partners, I would get sodium nitrate as an option. Sodium nitrate is soluble. My other possibility is lead 2 bromide. this is insoluble. So if the conditions are right and I get a precipitate, that precipitate would be lead 2 bromide. And we have a KSP value. I can go look up the KSP value for this salt. So, right, considering nothing else, lead bromide is my precipitate. However, if the solution has is big enough, right? If there's enough water, it's possible that we end up with an unsaturated solution, which means that the lead bromide can continue to dissolve. So what we're looking at is, will the solution, when I pour everything together, reach a point at which precipitation would be triggered? And we know when that happens using Q. So Q, precipitation is moving to the left. The point at which a reaction starts moving to the left is the point at which it goes from Q being equal to KSP to Q being greater than KSP. So one molecule past Q equals KSP, and we are at Q is greater, and we get a precipitate. So what we can do is we can take the concentrations we have and find Q and then compare it to the KSP. Right? When I dump all of this in solution, what are my concentrations going to be? Well, concentrations are what go into the Q expression. So lead bromide, if I'm dealing with KSP, the equation that I need is it going into solution. So equilibrium arrows required because it's an equilibrium. Lead 2 plus, 2 Br minuses. My Q expression, it's the lead concentration times the Br concentration squared. And we're given those values here. We're given the final concentrations, the 0.0150 and the 0.00350, the latter of which gets squared. That is my Q value, which is 1.84 times 10 to the minus 7th. Compared to KSP, it's less than the KSP. So no precipitate forms in this case. When I prepare it, it is an unsaturated solution. I could put more into solution, so there is no precipitate. All right, selective precipitation. This is just manipulating which precipitates first. So depending on the type of analysis you're doing or what you want to know about a sample, you may want to find the concentration of one ion before another. You may want to say precipitate out one of them and just filter the solution to remove it so that you can maybe get something, right? Like if you could precipitate a contaminant from drinking water, for example, that you would want to precipitate that but not anything else in the water that is either fine to be there or beneficial to be there. So let's look at a solution that has a magnesium 2 plus concentration of 0.059 molar and a calcium 2 plus concentration of 0.011 molar. We have that one with those ions. We're going to take a second solution that has potassium hydroxide and add it to the first one to precipitate these ions. And the first question is, which ion would precipitate first? So, well, it's the least soluble. So whichever is less soluble will fall out of solution first. And very nicely, since these have the same charge, right? So think if we're adding potassium hydroxide, what would precipitate? Well, it'd have to be magnesium hydroxide and calcium hydroxide. They have the same stoichiometry. So very nicely, we can compare the KSPs, or you could take the extra step to calculate the molar solubility, but you should get the same answer. The magnesium hydroxide is less soluble than the calcium hydroxide, so the magnesium hydroxide would precipitate first. So first question then after this is, what is the minimum hydroxide concentration that triggers precipitation? So the precipitation happens right when you go past that Q equals KSP point. So if we calculate the OH minus concentration when Q equals KSP, what we technically have is the point at which beyond it you would get precipitation. So one, probably even less than a drop, but one molecule more, one ion more of OH minus, and this is going to start precipitating. So Q equals KSP. The Q expression, magnesium concentration, OH minus concentration squared, set equal to the KSP. I know the magnesium concentration, right? It was one of the given parts of the problem, and it wants me to solve for what is the OH minus concentration when this precipitation starts. So OH minus is my only unknown. This would happen when the OH minus concentration is 1.9 times 10 to the minus sixth. Now it would be fair to write OH minus concentration greater than 1.9 times 10 to the minus sixth to be technically and officially complete, but you can say that it's equal to this concentration. This would be the tipping point. So as soon as we go just beyond this tipping point, that's when you would get precipitation.